All right, so let us begin a bit again so that it is recorded for you. Yeah, so now we are seeing how Gauss Seidel method it can work. How Gauss Seidel method can work. Okay, so this is a condition that is a necessary sufficient condition for the Gauss Seidel method to work. Is it needs the coefficient matrix A to be diagonally dominant. Okay, now what is meant by diagonally dominant? I told you here in this example that if you have this matrix A, then the diagonal elements, that is AII, okay, the absolute value of AII for each row should be greater than remaining elements of that row. So you can see A11, determine the mod of A11 should be greater than the sum of the remaining elements. Okay, that you can just write as sum of the Aij over j only. J equals to 1 to n, and you cannot take j equal to I because A11 is already there. Yes. So that's how we are trying to understand the diagonal dominance matrix. Okay. So if your matrix is diagonally dominant, then it is guaranteed that your iterative scheme of Gauss Seidel will definitely converge. And that's what we are trying to see in Python. Let us see over in Python. Yes. So you can see this in Python. Let me go to the Gauss Seidel scheme. Yes. So see this row here. Okay. See this row here. We have this matrix. First row is 8, 3, minus 3. Second row is minus 2. Then 5. Yes, the louder answer is in front. Then the third row is 3, 5, and 10. Okay. Now we are checking if this coefficient matrix is diagonally dominant or not. What we do, we first compute. First, we save this diag in this diagonal matrix. Diag is np.diag, where you can extract these diagonal elements from this matrix. And we are taking out this absolute value, np.abs. That is like absolute values of this matrix. Okay. A. Now, your job is to find the row sum without the diagonal element. Okay. So, which I wrote in the summation sign. You can see np.sum. np.sum, that is the summation you are doing. And then you have this np.absa. Okay. Since you are taking the diagonal element inside this, okay, so you are subtracting the diagonal element. Understood this, right? Understood? So you're taking the sum of all the absolute values of the rows. But you should know that while taking it, you are already taking the diagonal element. So therefore, we are subtracting the diagonal element here. Okay. Now we are just checking. Now we are just checking if diag is greater than off diag. Okay. Off diag consists of all the elements except the diagonal. Okay. Sum of all those elements except the diagonal for each row. Okay. Then you are just checking it. So this, why this is working so nicely? Because you are doing a verification here. You are not using a for loop to check each row greater than this, a second row greater than this. No. You are saving all of the diagonal elements in a matrix and also the sum in a vector. And you are just checking the vector. What it will do, it will check the corresponding elements of the vector. First row diagonal element greater than the remaining elements of the diagonal element. Yes, go to the second row. Second row, a diagonal element greater than the remaining elements. Yes, then the third row. All is done in diag. I urge you, when I share this, print the diag. Okay, print the diag vector and also print of diag vector. Okay, those will be two vectors. Those will not be numbers. I suggest you. Those will not be numbers. Diag and off diag will not be numbers. They will be the vectors. So therefore, just by this line, 2-3 lines, your code is working. So this matrix is diagonally dominant. You can check this. Now let us return to Gauss Seidel method, where you apply this. Did I same? No. Yes, I think we have taken the same matrix. 8, 3, minus 3. Yeah, 8, 3, minus. So we have taken the same matrix. So what we are actually solving is I'll write on the board. Actually solving is this 8x1 minus plus 3x2 minus, then I think minus 2x1 minus 8x2 plus 5x3, right? Then third one is 5x2 plus 10x3, right? Okay. The right hand side we will know from this equation. Sorry, I did not write this. I don't know why. Yes, you can see this is 14.5. Yes, so we are trying to solve this system of equations using Gauss Seidel method. Okay, and this is the program for it. Okay, what you were doing for in by hand, that's what we are doing by using Python computationally. Okay. How? So you already know there will be three solutions: x1, x2, x3. That I am initializing it to 0. Fine. Epsilon is taken to be 0.01. That is our stopping criteria. Somewhere you need to stop, right? You cannot go on forever. So epsilon is the stopping criteria. Converged equal to is set to false. So when it is converged, it will be true and it will come out. Okay, don't worry about this statement right now. And I'm storing all the solutions in a vector. Okay, you can see np.array. It's a vector. All the three solutions, x1, x2, x3. In this line, I am storing it in an array as x old. Okay, x old is that vector over there, which consists of all the solutions. Fine. Then I'm printing iteration and then the iteration number and the corresponding value of x1, x2, and x3. Okay. Fine. Let us see. Then I'm using our Gauss Seidel method. Just Gauss Seidel method. Can you appreciate how you wrote x1? You took these two quantities on the right hand side, then you divided by 8, isn't it? Can you see that happening over there? Can you see what is written in this equation line? Is everyone understanding this? This line, x2 and x3, just through this equation. x2, take minus 2 x1 on the right, 5 on this, divided by minus 8. Yes. So you can see everything is written over here. All these are written over here. Then I'm storing that x value. Can you appreciate that? Can you appreciate that? That will be the updated one. That will be the updated one. Why this is Gauss Seidel method? Because see, x1 you are computing here. The same variable you are using it here. That is the fresh. Huh? The denominator is -5, right? Here should be -5, you are telling, right? Is it correct now? It's correct now? It's correct, okay? Yeah. Okay. So this is Gauss Seidel method. Are you appreciating it? Can you see how we are storing the fresh values? This x1, which is newly computed, the hot fresh value of x1, okay, that you are using in the next step while calculating x2. Isn't it? X2 is depending on x1 and the same value which is computed here, you are using it here. That is what Gauss Seidel does, right? Gauss Seidel likes it fresh. So we are, and similarly x3 is depending on x1 and x2. Is it the old x1 and x2? No. These are the fresh one, which are just computed before the two lines. Are you understanding that you are doing fresh computations here? This is Gauss Seidel and not Jacobi method. Can you understand this is not Jacobi? That said, everyone understood? Understood? Yeah. Why this is Gauss Seidel? Understood? Gauss Seidel? Why this is Gauss Seidel? No, because x2 is just taking the updated value of x1. Is this x1 the old x1? I'm asking you. The x1 used in x2 expression, x1 used in x2 expression, is this the old x1 or the new x1? New x1. If it is a new x1, is this a Jacobi method or Gauss Seidel method? Yes, that's what we are telling. Okay, that's what we are telling. I hope you got this idea. Hmm? Then nothing else. You are just checking the dx quantity over here. I told you, if your quantities is converging, right? If your quantities are converging, let me get back to what you gave me the answer as. You see, your values are converging here, isn't it? 1.0005, 1.00005. Each component is converging towards itself, right? So how you know they are converging? Take the difference between the consecutive elements. Yes, take the difference between should be less than epsilon. Are you appreciating this? I'll come. Wait. This difference is less than epsilon. Are you appreciating this? That is the stopping criteria. If that is happening, then you stop. If that is not happening, then you keep on iterating till they are converging, right? I hope you are getting. You have to tell me that you are getting. Response. So that's what we are doing here. X minus X old. X minus X old. Okay. So it is just checking if it is less than that epsilon. Epsilon is 0.001. So if two decimal places, why 0.001 is special? 0.001 is special because if your roots, if your solution is approximating just to two decimal places, then you are done. Then you stop the method. I can also do for 0.001, 0.1 up to me. But then your number of iteration will increase because you are asking more accuracy. Okay. Hope you are getting it. Okay. So you are checking this quantity. If it is less than epsilon, yes, then it is true for you. Then converged. Then it is converged. Okay. Break. Else the loop keeps on growing. Else the loops keeps on growing. And how many maximum iterations can it take? Can you tell me? How many maximum iterations will it take? 50. You have written 50 for k equals to 1 to 50. So 50 iterations it will take. It is not necessary that it will go 50 iterations. It might be finishing before 50 iterations. If this condition is satisfied, dx is less than epsilon. Yes. If you are reaching convergence just before 50 iterations, then you should stop there, right? Why you should go ahead, isn't it? Yes, it's like the same thing I will tell you. Your bucket is there, right? You're filling water in the bucket. Okay. So water is totally available in your flat. Yes, you can use water, but you will use that much amount of water till your bucket is full, right? If the bucket is full, you will not pour more water, right? Why do the additional work? That's what I'm telling you. Okay, that's what the solution is. If this condition is satisfied, then break. Then you are done. Everyone appreciating it. Okay. So that's how it is. I am printing down all the iterations and you can see it over here. Can you see one very nice thing? Whatever I told is in this data set. So what is happening in this? Can you see that the iteration is first iteration, second iteration? You can see solution for both the first iteration and the second iteration are a bit different. It's a 1 point difference. You can see 1.7 then 2.7. One difference is 1, which is very high. But as you see below, as you go on increasing the number of iterations, take the example of 13th iteration and 14th iteration, almost equal values, isn't it? 0.1 difference, 0.01 difference. So therefore, we stop here. That's the criteria we set. Okay, that's the criteria we set. Okay, let us do an experiment. Let us try to increase the tolerance. Okay, that means I am not satisfied with 0.01 criteria. I want my solution to be more nicer. That is more accurate. That is 0.001. Okay, it should be 0.001 close to the accurate solution, to the analytical solution I want. So there I have to increase the number of steps. Okay, let us increase to 100. Let us run it. Of course, it will take a bit more time. It is not running actually. For your kind information, it is initializing the Python for this. Oh no. What happened here? Uh, all right, because I did not run the previous code. Oh no. Hang on. So every time you have to do this, import numpy as np. Yes, now it worked because in the later case you are using np.array, right? So you can see within 19 steps it converged here this time. Already to 20 iterations it need maximum. Nothing more than that. But can you appreciate the fact? Can you appreciate the fact that I told computer to run for 100 iterations, but the solution already converged before 20 iterations. So therefore it did not go up till 100. Okay, if you go till 100, you are just doing extra work, nothing else. Because you already reached your destination at 20 iterations. Yes. So that's the idea behind. You can see I have made it 100 iterations itself. Can you appreciate now that the solution is very accurate till 0.001 steps? Can you see? Can you compare the value? Compare the values between 18th iteration and 19th iteration. And see the difference. Is the difference less than 0.001? Previously, it was not the case. Previously, it was not the case. Now, let us do one more experiment. Okay. I am not even happy with this 0.001. I want it to be more accurate. Okay. This much. Let us see. Converged. But you can see now that now it takes more iterations. Now it took more iterations to reach to the solution, right? Previously, 0.001 convergence was taking 19 iterations, but 0.401, that much accuracy, 10 to the power minus 4 accuracy, is taking 30 iterations to converge. Still not 100. Still not 100 iterations. Less than that. Only 10 more iterations it took. So I hope you can appreciate that fact that in order to get more accuracy, you need more number of iterations. Okay. And Gauss Seidel is quite fast enough. Only 30 iterations it is taking. Did with Jacobi method easily if more than 50 iterations. Okay. It's clear, right? So we can solve this equation as well. No worries. I discussed all this in the last class. Okay. Fine. Where is my... So next we will discuss something new. Okay.